6.5, graph square root and cube root functions. The parent function for the family of radicals is f of x equals the nth root of x. Radical functions can be written in the general form y equals a times the nth root of x minus h plus k. The domain of radical functions with even indices, which is the plural of index, is x is greater than or equal to h, whatever h is. The range of radical functions with even indices is y is greater than or equal to k, or if a is less than 0, it'll be y is less than or equal to k. So if you have a negative number out here, your sign flips here for your inequality. If your index is odd, then your domain is all real numbers. Remember, the symbol for that is like a paragraph sign, but an R. And the range for all radical functions with odd indices is all real numbers again. Example 1. Graph 1/2 square root of x and state the domain and range. Compare the graph with the graph of y equals the square root of x. So let's start by graphing our parent function, which is y equals the square root of x. So we have our x values and our square root of x values. So if x is 0, then the square root of 0 is 0. If x is 1, the square root of 1 is 1. Then the next number where a square root will come out clean is 4. The square root of 4 is 2. So 0, 0, 1, 1, 4, 2. And then the next one will be 9, 3. So there is our parent function. So now we are going to graph 1/2 the square root of x. So when x is 0, the square root of x is 0, and half of that is 0. So this point will stay the same. Then this one, square root of 1 is 1. Half of that is 1/2. So we're going to go to 1, 1/2, which will be about there. And then the square root of 4 is 2. Half of that is 1. So 2, 1. The square root of 9 is 3. Half of that is 1 and 1/2, or 1.5. Oops, this should be out here at 4, 1. 4, 1. And this should be at 9, 1.5. There we go. So here is our function 1/2 the square root of x, and this one is the square root of x. Okay, so we graphed our function. Now we have to state the domain and range. So our index on a square root, since it doesn't have a number here, it is a square root, and square root means our index is 2. So our index is even. So our domain is going to be x is greater than or equal to h, where h is the number with x under the root. There's no number under the root here with x, so it's just 0. So x is greater than or equal to 0. And if we look at our graph, we start at 0 and go bigger than that. And then our range, our index is still even. We do not have a negative number out front here, so we stick with this one. So it's y is greater than or equal to the number added or subtracted outside the square root. We do not have one, so it is 0. And then compare the graph with the graph of y equals the square root of x. So we graphed y equals the square root of x, and we graphed y equals 1/2 the square root of x. And we can tell that the graph of 1/2 square root of x is a little bit shorter. So the mathematical terminology here is it's vertically compressed by a factor of 1/2. So basically, if the number out front here is a fraction less than 1, then it is vertically compressed. If it's greater than 1, or less than -1 if it's negative, then it's vertically stretched. So now, transformations. Oh, skipped a page. Example 2. Graph y equals -3 cubed root of x and state the domain and range. Compare the graph with the graph of y equals the cubed root of x. So, we are going to graph our parent function first. So our x's and our cubed roots of x. So let's do -8 as our first number. And -1, and then 0, and then 1, and then 8. Because those are the numbers that will come out clean. Okay, the cubed root of -8 is -2. So we're going to go to -8, -2. Put a dot. The cubed root of -1 is -1. Cubed root of 0 is 0. Cubed root of 1 is 1. Cubed root of 8 is 2. So we're going to plot these points, -1, -1, 0, 0, 1, 1, and 8, 2. Let's actually hit all of our points. There we go. Okay, so there's our graph. It's kind of a squiggle here. Now, we are going to do -3 times the cubed root of x. So, when the cubed root of x is -2, the -3 times that is going to be a +6. So we're going to go to -8, +6. When the cubed root is -1, -3 times that is a +3. So we're going to go to -1, +3. -3 times 0 is still 0, so 0, 0 is still on our graph. -3 times 1 is -3, so get a 1, -3. -3 times 2 is -6, so we're going to go to 8, -6. So it is a much bigger curve like that. So now we have to state the domain, range, and compare it to the parent function. So our index is odd, so our domain is all real numbers, and our range is all real numbers. And if you look at your graph, it goes on forever this way, it goes on forever this way, it goes on forever up. If you go out far enough, it's going to go that way, and same with down. So our domain and range are both all real numbers. Now, if we look at our original graph, it starts down here and goes up, and it's also a much smaller curve than this one. So, the first thing this one does is it's reflected over the x-axis, then it's vertically stretched. Remember, if this is a bigger than 1 number, then it's vertically stretched by a factor of 3. And the negative is what makes it reflected over the x-axis. So that is how we describe the comparison between our parent graph and our new graph. Now, example 3. The period of a pendulum is the time the pendulum takes to complete one back and forth swing. The period, t, in seconds can be modeled by t equals 1.11, the square root of L, where L is the pendulum's length in feet. Use a graphing calculator to graph the model. So we're going to get out our graphing calculator. There we go. And then we are going to hit y equals and do 1.11. Glare's bad here. That's better. Okay. So 1.11, the square root of L, or in this case x. Then we're going to graph it. So here is our function, and t is in seconds, so that's our y, and then L is our x. So we want to know how long is a pendulum with a period of 3 seconds. So we're looking for where y equals 3. So I'm going to hit trace, and I'm going to keep going until my y gets to about 3. That's pretty close. Somewhere between 7.27 and 7.42, so I'm going to guess 7.3, and that gets me real close. So I'm going to say that x is about 7.3 feet. Now we're on to transformations. So, to sketch a graph of y equals a times the nth root of x minus h plus k, follow these steps. First step is to sketch a graph of y equals the nth root of x. If a is negative, second step, reflect the graph over the x-axis. Step 3 is to stretch or compress the graph vertically by a factor of a. 4 is move the graph h units to the right and left if there's a plus sign here, and move the graph k units up, down if there's a minus sign here. Okay, so we are going to graph this function here. So, first thing we are going to do is graph the square root of x. So, the square root of 0 is 0. The square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. So there is step 1. Okay? Now, if a is negative, which it is, we reflect the graph over the x-axis. So this stays at 0. This becomes a negative 1. This becomes a negative 2. And this becomes a negative 3. So that was step 2. And step 3. Stretch or compress the graph vertically by a factor of a. So in our example here, a is 2. So we are going to multiply each of these by 2. So 0 stays at 0. Negative 1 goes to negative 2. Negative 2 goes to negative 4. And negative 3 goes to negative 6. So that's step 3. Now, step 4. Move the graph h units to the right or left if there's a plus sign. So we have a minus sign, so we are moving it to the right. So this point is going to move 3 to the right. This point is going to move 3 to the right. This point is going to move 3 to the right. And this point is going to move 3 to the right, which will make it off the paper. So this is step 4. And then our last step is to move the graph up or down. So we have a plus here, a plus 2, so we're going to move it up. So this is our graph number 4, so we're going to move this up 2. So here, 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 and then off the paper. So this, right here, this darkest one, is our final graph. That one's step 5. Now we have to state the domain and range. So again, if there's no number here, our index is 2, so it is even. So our x is greater than or equal to our h, which here is 3. If you look at the graph, we don't have any dots over here on our final graph until we get to 3. And then it's everything bigger than that. So x is greater than or equal to 3. And then our range, because a is negative, we're going to have to flip our sign. So it's going to be y is less than or equal to, and then it's this number right here, so 2. And if we look at our graph, we don't have any numbers up here. Our first dot is down here at 2. and then it goes down from there. So y is less than or equal to 2. And last example, example 5. Now, because I allow you to have calculators on the test, you can use a shortcut instead of using all 5 steps and just graph it on your calculator. So 3, and then the cubed root, we hit math. We go down to the cubed root of x plus 4 minus 1. Okay, then I'm going to trace. And I'm going to try to find numbers that are pretty. So, start at -9. Nope. -8. Nope. 7, -6, -5. Okay, so -5 is at -4. Okay, and -10 is somewhere down here. So like that. -4 is at -1. -3 is at +2. So our curve does that. And then -2, nope, -1, 0, 1, 2, 3, 4 is at 4, 5. 4, 5. So that is my curve. Now, the domain and range, our index is odd. And for odd functions, our domain is all real numbers, and our range is all real numbers. So we are done with that problem.